The morning of December 22, 1944, somewhere along the road between Bastogne and Oberfeldwebel, a German Panther tank sat motionless in the snow. Its engine, a Maybach HL 230P30 that produced 690 horsepower, was silent. Not because it had been destroyed by enemy fire. Not because it had run out of fuel, though that was becoming an increasing problem. The engine was silent because the final drive had failed. Inside the tank, Oberfeldwebel Heinrich Müller stared at the instrument panel with a familiar mixture of frustration and bitter resignation. This was the second Panther he had lost to mechanical failure in 3 weeks. The first had thrown a transmission gear outside of Schmidt. Now this one, with barely 200 kilometers on the replacement final drive, had seized up completely. The tank could not move forward or backward. It could rotate its turret, traverse its 75mm gun, and fire accurately at targets over a mile away. But it could not move. Through his vision port, Müller watched an American tank column pass on a parallel road approximately 800 meters to the south. Sherman tanks, probably from the 4th Armored Division pushing to relieve Bastogne. He counted them, 6, 8, 11 vehicles moving in formation. Their engines, he knew from intelligence reports, produced only 500 horsepower, nearly 200 horsepower less than his Panther's Maybach. They were inferior machines on paper. Undergunned, underarmored, built by a nation that supposedly valued quantity over quality. But they were moving. And his tank, with its superior gun and superior armor and superior engine, was not. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Müller's crew had already begun the familiar routine. The driver had attempted to reverse, trying to break whatever had seized in the final drive mechanism. That had failed. The radio operator had contacted battalion headquarters, reporting their position and status. The response had been predictable. Disable the tank and fall back on foot. There were no recovery vehicles available. There were no spare parts. There was no time. They would have to destroy their own tank to prevent its capture, not because the enemy had defeated them in combat, but because German engineering had defeated itself. The Panther OSG they were abandoning represented the pinnacle of German tank design. It mounted a long-barreled 75mm KWK-42 gun that could penetrate any American tank at ranges exceeding 2,000 meters. It had sloped frontal armor 80mm thick, angled at 55 degrees, providing effective protection equivalent to roughly 140mm against anti-tank fire. Its Maybach engine could theoretically push the 45-ton tank to speeds of 46 km per hour on roads. On paper, it was vastly superior to the American Sherman Easy-8 that Müller was watching through his optics. The M4A3E8, as the Americans designated it, had only 76mm of frontal armor, barely half the effective protection of the Panther. Its 76mm gun, while improved over earlier Sherman variants, still struggled to penetrate Panther armor from the front at combat ranges. Its Ford V8 engine produced that modest 500 horsepower. Yet those American tanks kept moving. They moved through Belgium in the snow. They moved through France in the mud. They moved through the Siegfried Line fortifications and across the German border. They moved day after day, requiring only basic maintenance that their crews could perform in the field with standard tools. When they did break down, which was rare, American recovery vehicles would have them back in action within hours. The confidence German tank crews felt in their machinery was not unfounded delusion. It was built on genuine technological achievement in years of careful engineering development. When the Panther tank entered production in 1943, it represented the cutting edge of armored warfare design. Every aspect of the vehicle reflected German engineering philosophy that had dominated industrial thinking since the late 19th century. Precision, performance, and technological superiority. The Maybach company, which produced engines for German tanks, had a pedigree extending back to the earliest days of automotive development. Wilhelm Maybach had worked with Gottlieb Daimler in the 1880s, creating some of the first high-speed internal combustion engines. The Maybach HL 230 engine that powered the Panther was a direct descendant of that engineering tradition. It was a V12 configuration, water-cooled, with aluminum alloy construction to save weight. Each cylinder displaced nearly 2 liters. The total displacement was 23 liters, or roughly 1,400 cubic inches in American measurements. The engine achieved its 690 horsepower output at 3,000 revolutions per minute. By the standards of 1944, this was remarkable specific power output from a naturally aspirated engine. German engineers had optimized every aspect of the design for maximum performance. The fuel injection system precisely metered gasoline to each cylinder. The valve train used overhead camshafts for efficient breathing. The cooling system circulated large volumes of coolant to manage the tremendous heat generated by high-power operation. But performance came at a cost that was not immediately apparent in the design specifications. The Maybach required extremely precise manufacturing tolerances. The crankshaft, connecting rods, and pistons had to be machined to exacting standards and assembled by skilled technicians. The fuel injection system needed precise calibration. The cooling system relied on gaskets and seals that had to be made from specialized materials. Any deviation from specifications, any shortcut in manufacturing, any substitution of materials, would result in reduced reliability or catastrophic failure. Germany in 1943 and 1944 was a nation increasingly unable to maintain those standards. Allied bombing had damaged machine tool factories. Skilled workers had been conscripted into military service. Critical materials, particularly molybdenum and chromium for steel alloys, were in short supply. Factories that had once produced engines in climate-controlled facilities with stringent quality control now operated in bombed-out buildings with substitute materials and inexperienced workers. The Panthers rolling off production lines at MAN in Nuremberg, Daimler-Benz in Berlin, and Maschinenfabrik Niedersachsen in Hanover were not the precisely engineered machines the designers had envisioned. They were compromise vehicles, built as quickly as possible with whatever materials were available. The Maybach engines installed in these tanks often had subtle manufacturing defects that would not reveal themselves until the tank had been in operation for a few dozen hours. The transmission, an even more complex piece of machinery, suffered similar problems. The Panther used an AK-7-200 transmission, a 7-speed gearbox with a synchromesh design that allowed smooth shifting. In theory, this transmission was superior to the simpler designs used in Allied tanks. In practice, it was a maintenance nightmare. The gears required precise heat treatment to achieve the necessary hardness without becoming brittle. The synchronizers needed exact adjustment. The entire assembly had to be properly lubricated with specific grades of oil. The final drive, the mechanical system that transmitted power from the transmission to the drive sprockets that moved the tracks, represented perhaps the most critical weakness in the entire Panther design. This component bore enormous stress during operation. Every time the tank accelerated, every time it climbed a hill, every time it turned, massive torque loads passed through the final drive gears. German engineers had calculated the loads based on the tank's weight and expected operational conditions. They had designed the final drive with what they believed were adequate safety margins. But their calculations had not fully accounted for the reality of combat operations in 1944. Panthers were often operated at maximum power for extended periods. They climbed steep hills in the Ardennes forest. They traversed rough terrain where the tracks encountered obstacles that created shock loads far exceeding design specifications. They operated in cold weather that made lubricants viscous and metal brittle. The final drives began failing at alarming rates. Early production Panthers, rushed into service at the Battle of Kursk in July 1943, experienced catastrophic failure rates. Entire units reported that more than half their tanks had broken down before reaching the battlefield. The problem was so severe that Hitler himself was briefed on it, and he ordered immediate design improvements. Engineers increased the diameter of the final drive gears, improved the heat treatment process, and specified better lubricants. These modifications helped, but they did not eliminate the fundamental problem. The Panther was a heavy tank, 45 tons, with an engine that produced high power but also high stress on the drivetrain. The final drives, even the improved versions, had a service life measured in hundreds of kilometers rather than thousands. Tank crews learned to be gentle with their machines. Experienced drivers avoided sudden acceleration. They shifted gears smoothly and carefully. They tried to minimize sharp turns that placed maximum stress on the final drives. But combat operations did not allow for gentle handling. When enemy tanks appeared, Panthers had to maneuver aggressively. When infantry needed support, they had to climb hills and cross ditches. The machines were operated at the limits of their capability, and they broke. The psychological impact on German tank crews was profound. They had been told they were operating the best tanks in the world. Propaganda films showed Panthers crushing Soviet T-34s, destroying American Shermans at long range, breaking through Allied lines with unstoppable power. And in direct combat, when everything worked, the Panther was indeed a formidable weapon. Its gun could kill any Allied tank it encountered. Its armor could resist most Allied anti-tank weapons from the front. But increasingly, German tankers found themselves abandoning perfectly functional guns and armor because the mechanical systems that moved the tank had failed. They sat in disabled vehicles watching Allied tanks drive past. They destroyed their own machines to prevent capture. They walked back to German lines carrying their personal weapons, leaving behind tons of sophisticated machinery that had become useless steel. Some crews began to question the entire philosophy behind German tank design. Was raw performance worth the reliability problems? Would a simpler, more robust design have been more effective even if it sacrificed some technical superiority? These were dangerous questions in the German military where faith in superior technology was an article of doctrine. The American tank that German crews watched driving past their disabled Panthers was the M4A3E8 Sherman, a vehicle that represented an entirely different engineering philosophy. Where German designers had pursued maximum performance, American engineers had optimized for reliability, maintainability, and mass production. The result was a tank that looked inferior on paper but proved superior where it mattered most, in sustained combat operations. The M4A3E8 designation requires explanation. M4 indicated the basic Sherman design. A 3 specified the engine variant, in this case the Ford GAA V8. E8 denoted the improved suspension system with horizontal volute springs and wider tracks, hence the nickname Easy-8. The complete vehicle weighed approximately 33 tons in combat configuration, 12 tons lighter than the Panther. The Ford GAA engine was a masterpiece of practical engineering. It was a 90-degree V8 configuration, water-cooled, with a total displacement of 18 liters or roughly 1,100 cubic inches. The engine produced between 450 and 500 horsepower depending on tuning and altitude, considerably less than the Panther's Maybach. But the GAA had been designed with entirely different priorities. Ford Motor Company had developed the engine specifically for tank use in 1942. The design team, led by engineers who had spent decades building automotive engines for mass production, understood that a tank engine needed to be simple enough for field maintenance, robust enough to survive abuse, and manufacturable in quantities that would support a global war. They created an engine with fewer parts than the Maybach, wider manufacturing tolerances, and the ability to run on lower quality fuel. The GAA used a simple but effective valve train with pushrod-operated overhead valves. This design was less efficient than the Maybach's overhead camshaft system, but it was far more reliable and easier to service. A mechanic could adjust the valves with basic hand tools in the field. The fuel system used a single updraft carburetor, again simpler and more reliable than the Maybach's fuel injection. The ignition system used 2 magnetos, providing redundancy. If one failed, the engine would continue running on the other. Ford built the GAA with generous clearances between moving parts. German engineers might have viewed this as sloppy work, accepting lower performance in exchange for easier manufacturing. But those clearances meant the engine could tolerate dust, dirt, and debris that would have destroyed the precisely fitted Maybach. They meant the engine could run even when oil pressure dropped due to a minor leak. They meant thermal expansion during operation did not cause binding or seizure. The transmission paired with the Ford GAA was the synchromesh type, a 5-speed gearbox that was less sophisticated than the Panther's 7-speed unit but exponentially more reliable. American tankers learned they could shift gears roughly, even grinding them occasionally during combat, without causing failure. The transmission contained fewer gears, used simpler synchronizers, and could be rebuilt by unit mechanics using standard spare parts that were available throughout the supply system. The final drive on the Easy-8 was overbuilt by German standards. American engineers had calculated the maximum possible loads, then designed the final drive to handle twice that stress. The gears were cut from high-quality steel with proper heat treatment, but the design did not rely on perfect manufacturing. If the steel was slightly softer than specification, the final drive would still function. If the heat treatment was not perfectly uniform, the gears would still survive. This design philosophy extended to every system on the Sherman. The suspension used horizontal volute springs, heavy coils of steel that absorbed shock through simple compression. They were crude compared to the Panther's torsion bar suspension, but they were nearly indestructible. What a Sherman threw a track, the crew could usually repair it in less than an hour using tools carried on the tank. When a Panther threw a track, it often required specialized equipment and several hours of work. The Sherman carried more ammunition than the Panther, 97 rounds of 76mm compared to 79 rounds of 75mm. It had better crew accommodations with more space to move and work. It had superior vision equipment with periscopes that provided good situational awareness. And most critically, it had a radio in every tank, not just in command vehicles. This allowed coordination that German tanks could rarely achieve. American tankers learned to trust their Shermans in ways German tankers never could trust their Panthers. When a Sherman crew buttoned up and drove into combat, they knew with near certainty that their tank would continue functioning throughout the engagement. The engine would not overheat. The transmission would not fail. The final drive would not cease. They could focus on fighting rather than nursing a temperamental machine. The Battle of the Bulge in December 1944 provided a massive field test comparing German and American tank reliability under identical conditions. Both sides operated in the same brutal weather, the same difficult terrain, the same fuel shortages. The differences in mechanical reliability became starkly apparent. German armored units assigned to the offensive, particularly the 5th Panzer Army and the 6th Panzer Army, began the attack with approximately 650 tanks including significant numbers of Panthers and the even heavier Tiger IIs. American intelligence initially underestimated these numbers, but captured documents and post-battle analysis confirmed the German commitment. Within the first 3 days of the offensive, German maintenance companies reported alarming breakdown rates. Panthers were failing at rates exceeding 20%. Not 20% total losses including combat damage, but 20% mechanical failures requiring major repair or recovery. The cold weather, with temperatures dropping below -10 degrees Celsius, exacerbated every mechanical weakness. Engine oil became viscous, making cold starts difficult. Transmissions ground through thick lubricant that had turned almost solid. Final drives, already stressed under normal conditions, cracked under the additional loads imposed by frozen ground and icy roads. Colonel Hans von Luck, commanding a Panzer regiment during the offensive, later wrote about the frustration of watching his tanks fail before encountering the enemy. His unit started the attack with 42 Panthers. Within 72 hours, only 28 remained operational. 5 had been knocked out in combat. 9 had broken down and been abandoned after crews determined they could not be repaired in time. The advancing German forces left a trail of disabled Panthers along the roads through Belgium. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The fuel situation compounded the mechanical problems. German planners had counted on capturing American fuel stocks to sustain the offensive. This was not merely hopeful thinking, it was essential to the entire operation. German fuel reserves were critically low. The Maybach engines in Panthers consumed fuel at prodigious rates, approximately 320 liters per 100 kilometers under combat conditions. That translated to less than 1 mile per gallon in American measurements. When German spearheads failed to capture fuel depots intact, their advance slowed. Tank commanders faced impossible choices. They could push forward aggressively, risking running out of fuel far from German lines. Or they could conserve fuel, moving cautiously, allowing American defenders time to reinforce. Either choice was bad. Many Panthers simply ran out of fuel and had to be abandoned, adding to the growing collection of disabled tanks littering the battlefield. American tank units, by contrast, maintained operational rates above 80% throughout the battle. The 4th Armored Division, racing north to relieve Bastogne, kept its Shermans running through days of continuous movement and combat. Crews performed basic maintenance during brief halts, checking oil levels, topping off fuel, inspecting tracks. The tanks kept moving. The 3rd Armored Division, fighting in the northern shoulder of the Bulge, reported minimal mechanical failures despite operating in the same conditions that were destroying German tanks. Their maintenance logs show routine work, oil changes, minor repairs, nothing catastrophic. The Ford GAA engines started reliably even in sub-zero temperatures. The transmissions shifted smoothly. The final drives handled the frozen terrain without failure. Lieutenant Colonel Creighton Abrams, commanding a tank battalion in the 4th Armored Division, pushed his Shermans hard during the relief of Bastogne. His tanks moved through the night in a snowstorm, navigating by compass in dead reckoning. They fought through German defensive positions in the morning, broke through to Bastogne in the afternoon, and remained combat-ready throughout. Not a single tank was lost to mechanical failure during this critical operation. The moment of realization for many German tank crews came not in a single dramatic event but through accumulated experience over days and weeks of the Ardennes offensive. They watched American tanks moving while German tanks sat disabled. They saw American recovery vehicles efficiently retrieving damaged Shermans and returning them to combat within hours. They observed American supply convoys bringing forward spare parts, ammunition, and fuel in quantities that seemed impossible given the distances involved. Hauptmann Werner Rahn, commanding a company of Panthers in the 1st SS Panzer Division, experienced this realization during the fight for Elsenborn Ridge in late December. His company had started with 14 Panthers. By December 23, only 6 remained operational. 3 had been destroyed in combat. 5 had broken down and been abandoned. 2 were being worked on by maintenance crews who lacked proper tools and spare parts. Rahn and his remaining crews occupied defensive positions watching American forces regroup after halting the German advance. Through binoculars, he observed an American tank maintenance area approximately 2 kilometers distant. What he saw challenged everything he had been taught about American industrial inefficiency and mechanical incompetence. American mechanics worked on several damaged Shermans in an organized, systematic manner. They had proper lighting powered by generators. They had spare parts stacked in organized piles. They had specialized tools for every task. Ron watched one Sherman that had thrown a track being repaired. A team of 4 mechanics worked for approximately 90 minutes, removed the damaged track section, installed a replacement, and had the tank running again before dark. The Sherman drove away under its own power, returning to combat operations. In Ron's company, they had a Panther with a thrown track that had been sitting for 3 days. His mechanics lacked the proper tools to disconnect the track pins. They had no replacement sections. They had no lifting equipment to handle the heavy track assemblies. The tank sat immobile, its guns still functional, its armor intact, but utterly useless because of a relatively minor mechanical problem. The contrast was devastating. Here was physical proof that German technical superiority meant nothing if it could not be sustained in the field. The Americans had built a system that kept their tanks running. They had trained mechanics who could perform repairs quickly. They had distributed spare parts to forward units. They had designed their tanks to be maintainable under combat conditions. Germany had done none of these things. Ron later described his feelings to American interrogators after his capture. He used the word Systemüberlegenheit, system superiority. He explained that he had finally understood the Americans were not winning because they had better tanks, they were winning because they had a better system. the tank was just one component. The mechanics, the spare parts, the supply chain, the training, the design philosophy that prioritized reliability over raw performance, all of these elements working together created overwhelming advantage. Other German tankers reported similar epiphanies. A Tiger II commander described watching American tank columns moving past his disabled vehicle. His Tiger mounted an 88mm gun that could destroy any American tank at extreme range. It had armor over 180mm thick that was nearly impervious to American weapons from the front. But it weighed 70 tons, and its transmission had failed after less than 100 kilometers of operation. The Tiger sat like a fortification while American Shermans that it could easily destroy in combat simply drove around it and continued their advance. A Panther driver who had operated tanks since 1943 told interrogators about his growing disillusionment. He had believed German propaganda about superior engineering and American mass-produced junk. He had trusted that quality would defeat quantity. But by December 1944, he had personally witnessed 3 Panthers break down under him. He had walked away from perfectly good guns and armor because the mechanical systems failed. He had realized that a tank that could not move was not a tank at all, it was an expensive pillbox that would eventually be bypassed or destroyed. By January 1945, the German offensive in the Ardennes had collapsed. The bulge created by the initial German advance was systematically eliminated by Allied counterattacks. German armored units withdrew eastward, back into Germany, leaving behind hundreds of disabled and abandoned tanks. American recovery teams counted the wrecks. Panthers outnumbered Tigers, and mechanical failures outnumbered combat losses in many sectors. The surviving German tank crews carried their knowledge back to the shrinking Reich. They told their stories in maintenance depots and replacement training centers. They described watching American tanks move while German tanks broke down. They talked about the abundance of American spare parts and the efficiency of American maintenance systems. They questioned, carefully and quietly, whether German engineering superiority was real or merely propaganda. These conversations were dangerous. Defeatism was a serious offense in the German military in 1945. Soldiers could be executed for spreading pessimistic assessments of Germany's chances. But the evidence was undeniable. German tank crews could see the reality with their own eyes. No amount of propaganda could change the fact that their tanks were failing at catastrophic rates while American tanks kept running. The maintenance records from German Panzer divisions in early 1945 paint a grim picture. The Panzer Lehr division reported that only 30% of its tanks were operational at any given time. The remainder were undergoing repair, awaiting spare parts, or abandoned due to irreparable damage. The 2nd Panzer Division, which had fielded over 100 tanks at the start of the Ardennes offensive, could muster fewer than 20 operational vehicles by February. Spare parts had become critically scarce. Allied bombing had destroyed many of the factories producing transmission components and final drives. The remaining factories struggled to maintain production with depleted workforces and limited raw materials. Even when parts were manufactured, transporting them to frontline units became nearly impossible as Allied air power interdicted German supply lines. German tank crews learned to cannibalize disabled vehicles to keep a handful of tanks operational. A Panther with a failed engine might donate its transmission to another Panther with a working engine but broken transmission. A third Panther might provide final drives, road wheels, and track sections. This practice kept some tanks running, but it was a losing battle. Each cannibalized vehicle represented irreplaceable combat power that could never be restored. Meanwhile, American tank units maintained operational readiness rates above 75% even during intense combat operations. The supply system delivered spare parts to forward maintenance units with remarkable efficiency. Ships crossing the Atlantic carried containers specifically packed with Sherman components, organized by part number, ready for immediate distribution. Trucks moved these parts from ports to depots to frontline units in a continuous stream. American maintenance doctrine emphasized speed and efficiency. If a Sherman suffered engine failure, mechanics did not attempt to repair the engine in the field. They removed the entire engine assembly using specialized lifting equipment, installed a replacement engine from stock, and had the tank operational within hours. The damaged engine went to a rear area maintenance depot where specialists could perform detailed repair work. This system, logistically complex but operationally effective, kept tanks in combat. German maintenance doctrine, by contrast, required field mechanics to diagnose and repair problems on individual tanks. This took time, required skilled technicians, and often proved impossible when proper tools or parts were unavailable. A Panther with a failed Maybach engine might sit for days or weeks waiting for repair parts that never arrived. Eventually, the tank would be destroyed by its own crew or captured by advancing Allied forces. The psychological toll on German tank crews deepened as the war approached its end. They had joined Panzer units believing they were part of an elite force equipped with the world's best tanks. They had trusted German engineering and German superiority. By spring 1945, they knew better. They were operating obsolete equipment that broke down more often than it fought. They were part of an army that could no longer supply or maintain its forces. They were losing. Some crews deserted, abandoning their tanks and walking away from the war. Others fought on with fatalistic determination, knowing defeat was inevitable but continuing to follow orders. A few still believed in German victory, clinging to propaganda about wonder weapons and strategic turnarounds that would change everything. But most simply endured, counting the days until either death or capture ended their service. The production statistics tell the story with brutal clarity. From 1943 through the end of the war in May 1945, German factories produced approximately 6,000 Panther tanks. This represented an enormous industrial effort for a nation under constant bombing and facing chronic shortages of raw materials and skilled labor. German leaders viewed the Panther as a war-winning weapon, and they committed substantial resources to its production. During the same period, American factories produced more than 21,000 M4 Sherman tanks in various configurations, including several thousand M4A3E8 Easy-8s. This production occurred while American industry simultaneously produced thousands of aircraft, hundreds of ships, millions of rifles, and vast quantities of ammunition, vehicles, and supplies. The Sherman was just one product in an industrial system operating at scales Germany could not match. But the numerical disparity understates the true advantage. German Panthers had an operational readiness rate that averaged between 50 and 60% under good conditions and dropped below 40% during intense combat operations. This meant that of 6,000 Panthers produced, only half were available for combat at any given moment, and that number declined as the war progressed and maintenance systems broke down. American Shermans maintained operational readiness rates between 75 and 85% throughout the war. Of 21,000 Shermans produced, nearly 18,000 could be expected to be combat ready at any time. The American supply system kept them running with spare parts, fuel, and ammunition delivered reliably to frontline units. The maintenance burden tells another part of the story. A Panther required approximately 30 man-hours of maintenance for every 10 hours of operation. This included routine maintenance like oil changes and track tension adjustments, plus frequent repairs to the temperamental transmission and final drive. A Sherman required approximately 10 man-hours of maintenance for every 10 hours of operation, a 3-to-1 difference in maintenance burden. Multiply that difference across thousands of tanks, and the strategic implications become clear. American armored divisions could keep more tanks operational with fewer mechanics. They could sustain high operational tempo without exhausting their maintenance personnel. They could fight continuously while German units had to pause for extensive maintenance periods. The fuel consumption disparity compounded these advantages. A Panther consumed approximately 320 liters of gasoline per 100 kilometers under combat conditions. A Sherman consumed approximately 240 liters per 100 kilometers, about 25% less. This difference, seemingly modest, meant Sherman units could operate on longer supply lines and conduct deeper advances without running out of fuel. American logistics could deliver the required fuel. German logistics, strained by Allied bombing and limited transportation capacity, increasingly could not. By early 1945, German tank units were sometimes immobilized not by mechanical failure but simply by lack of fuel. Panthers sat with working engines and functioning transmissions, useless because there was no gasoline to run them. The training system revealed another crucial difference. American tank crews received extensive training on maintenance procedures. They learned to perform basic repairs, change oil, adjust tracks, and troubleshoot common problems. Sherman design philosophy made these tasks relatively simple. Crew members could maintain their tanks with basic mechanical knowledge and standard tools. German tank crews received similar training, but Panther maintenance was far more complex. Adjusting the tension on the torsion bar suspension required specialized tools and careful measurement. Troubleshooting the Maybach engine required understanding of fuel injection systems and precise ignition timing. Working on the transmission demanded skills that most crew members did not possess. Panthers required professional mechanics for tasks that Sherman crews could handle themselves. Post-war analysis by American and British intelligence services examined captured German tanks and interviewed German tank crews and maintenance personnel. The reports concluded that German tank design philosophy had prioritized the wrong attributes. Raw performance, thick armor, and powerful guns mattered less than reliability, maintainability, and ease of production. The Americans had understood this. The Germans had not. One American armor officer, analyzing Panther performance after the war, noted that the German tank was superior to the Sherman in almost every measurable combat characteristic except the ones that actually mattered for winning a war. The Panther could not be produced in sufficient numbers. It could not be kept operational at acceptable rates. It could not be maintained by its crews in the field. It could not operate effectively on the logistics that Germany could provide. These failures negated its advantages in armor protection and firepower. In the decades after World War II, tank designers worldwide studied the lessons of the conflict. The debate between performance and reliability became central to armored vehicle development. German engineers, now working for NATO nations or in the rebuilt West German military, applied the lessons they had learned. The Leopard 1 tank, developed by West Germany in the 1960s, prioritized reliability alongside firepower and protection. It was a spiritual descendant of the Panther but engineered with American-style attention to maintainability. American designers continued the philosophy that had made the Sherman successful. The M48 Patton tank, the M60 tank, and eventually the M1 Abrams all emphasized reliability and ease of maintenance. The Abrams, fielded in the 1980s, could have its entire engine replaced in under 30 minutes by a trained crew using built-in lifting equipment. This design choice reflected lessons learned 40 years earlier when maintenance speed proved as important as combat capability. Soviet tank design, influenced by their own wartime experience with the T-34, also emphasized simplicity and reliability over pure performance. The T-54 and T-55 tanks that equipped Soviet forces during the Cold War were crude by Western standards but remarkably reliable and easy to maintain. Soviet designers understood that a tank that broke down frequently was useless regardless of its combat characteristics. The legacy of the reliability revolution in tank design extends beyond specific vehicles to fundamental questions about military technology and industrial warfare. The Panther represented the culmination of one philosophy: achieve technical superiority through advanced engineering and accept the costs in complexity and reliability. This philosophy assumed that superior performance would offset reliability problems and that skilled crews could compensate for maintenance difficulties. The Sherman represented a different philosophy: optimize for the entire system including production, maintenance, and logistics, even if this means accepting lower raw performance. This philosophy assumed that wars are won by keeping equipment operational and that reliability matters more than theoretical capability. World War II proved which philosophy was correct. Not through any single battle or engagement, but through the grinding arithmetic of sustained combat operations. German tanks broke down more often than American tanks. German tanks required more maintenance time. German tanks consumed more fuel. German tanks needed spare parts that were not available. German industry could not produce enough tanks to replace losses. German logistics could not sustain armored operations. These factors, far more than the relative thickness of armor or the muzzle velocity of guns, determined outcomes. American armored divisions kept moving while German panzer divisions ground to a halt. American tanks were on the battlefield while German tanks sat in maintenance depots. American crews trusted their equipment while German crews lost faith in theirs. The morning of December 22, 1944, when Oberfeldwebel Heinrich Müller sat in his disabled Panther watching American Shermans drive past, encapsulated this entire story. His tank, with its powerful Maybach engine producing 690 horsepower, could not move because the final drive had failed. The American tanks, with their modest Ford engines producing only 500 horsepower, kept running because they had been designed and built to run. Müller and his crew destroyed their Panther that morning, setting charges to disable the gun and burning the interior to prevent capture. They walked back to German lines, joining thousands of other tank crews who had abandoned disabled vehicles across the winter landscape of Belgium. Behind them, they left evidence of a failed philosophy, of engineering ambition that had exceeded industrial capability, of performance that came at the cost of reliability. The American tankers who drove past in their Shermans probably never knew about Müller's Panther sitting silent in the woods. They were focused on their mission, pushing forward to relieve Bastogne, to defeat the German offensive, to win the war. Their tanks kept running because someone, years earlier, had made fundamental decisions about design philosophy. Those decisions, more than any single battle or weapon, helped determine the outcome of World War II. The horsepower rating of an engine, it turned out, mattered far less than whether that engine would still be running after 200 kilometers of hard use. Technical sophistication meant nothing if it came at the cost of reliability. In an industrial warfare between modern nations, the ability to keep machines operational day after day, week after week, month after month, proved more valuable than any amount of raw performance. The German tank crews learned this lesson the hard way, sitting in disabled Panthers and Tigers, watching American and British and Soviet tanks move past them toward Berlin. It was a bitter lesson, paid for with lives and defeats, and it reshaped tank design for generations to come. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.